Hello, everyone. So this week we're going to be doing chapter 13. This is our second to last chapter of new stuff. All right, so keep it up. This chapter is called ethers, epoxides, thiols, and sulfides. It should really be called ethers, epoxides, and then nomenclature of thiols and sulfides, because that's really the only thing we're going to cover about thiols and sulfides, is how to name them, and then a few reactions which we've actually already gone over as to how to prepare them. Okay, so let's take these functional groups one by one. We're going to start by introducing ethers. So an ether, if we remember back to when we were learning functional groups, that is a functional group that has an oxygen in the middle, and then on either side of that oxygen are going to be some sort of hydrocarbons, right? So these R's are going to be carbons of some length, right? So different than an alcohol, of course, where this would be replaced not by an R group, but by an H. That would be an alcohol. So an ether is when that is some other carbon containing hydrocarbon chain. Those R groups can be anything. They can be an alkyl chain. They can even be aryl, meaning a benzene ring, or they can be vinyl, meaning a double bond. The only thing they can't be is what's called an acyl group. That'd be this right here, or a carbonyl is really what it is. If you have a carbonyl directly next to that oxygen, it's no longer an ether. That would be considered an ester. But as long as that isn't the case, it could be pretty much anything, and then it's still an ether. Okay, so how do we name ethers? So unfortunately, ethers are one of the ones where the common names have stuck quite a bit. Luckily, they're fairly easy to name according to those common names. So first of all, you look on either side of the oxygen and you name each R group. So in this case, that's 1, 2 carbons, so that'd be an ethyl group. On the other side is 1 carbon, so that's a methyl group. And then you just arrange them in alphabetical order, followed by the word ether, right? So this would be ethyl, methyl, ether. And these are common names, so you want to make sure to use the common names for those different branched alkyl chains. So for example, this would be tert-butyl on this side. Remember, this is the tert-butyl group, and then methyl. And again, arrange them alphabetically, followed by ether. You might be saying, well, tert starts with T, that's after M in the alphabet. Remember, we ignore those prefixes when we're assembling alphabetical order, except for iso. I don't know why iso is special, but it does count in terms of the alphabetical order. But remember those common names. So you might want to go back and review that when we were first talking about alkanes. Those were those tert-butyl, sec-butyl, isobutyl, isopentyl, iso anything really. Those are those common names that you want to make sure you have memorized here. Okay, so those would be how to name ethers using the common names. There's also the systematic, the IUPAC nomenclature. Okay, so how the IUPAC nomenclature works is to treat the ether portion as a substituent, right? So what do I mean by that? That means that the oxygen, as well as the other half of that carbon chain, is going to be considered the parent or the substituent, and thus the other portion is going to be the parent chain. So just like we did before when we're choosing our parent chain, the parent chain should be chosen as the longest contiguous set of carbons. So basically, you're going to look at your ether, you're going to look at which half's longer. That one's going to be the parent chain, and the other portion is going to, okay? So we have a 1, 2, 3, 4, 5 carbon parent chain or a pentane, and we have a 1, 2 carbon substituent. How we refer to these ether substituents is as alkoxy, right? So where alk would be replaced by the prefix of whatever the number of carbons is. So methoxy, ethoxy, propoxy, butoxy. The oxy ending is how you know that it is going to be that ether group. Okay, so this would be ethoxy pentane. Just to do another example. Okay, again, cut your ether in half, figure out which chain is longer. In this case, it's this 1, 2, 3, 4, 5. Nope, that's not 5, that's 6. So this would be a hexane. And then our ether group, our substituent, has 1, 2, 3 carbons. So this is a propoxyhexane. Okay. One of the nice things about ethers, at least with respect to the oxygen atom, is that the oxygen can only have 2 bonds. There are 2 lone pairs here, which means that you don't have to worry about it ever being a stereocenter. Yay. Okay, and then properties of ethers. So remember we were learning about alcohols and how they have these incredibly strong intermolecular interactions, and those are called hydrogen bonds because you have the hydrogen in the alcohol group that's bearing that partial positive charge. The oxygen has the partial negative charge. So when you have two molecules that are alcohols, they can sort of align themselves such that the hydrogen on one is talking to the oxygen on the other one, creating this nice strong hydrogen bond. Well, with ethers, we've replaced that hydrogen with an, we still have the oxygen still has its lone pairs. And so ethers can be hydrogen bond acceptors, but there's no donor there. Okay, so this is an interesting part about the properties of ethers. Because of that, their intermolecular interactions in a sample of ether are way weaker than they would be for an alcohol. So remember, we can use boiling point as sort of a measure of how strongly neighboring molecules are interacting with one another. If we take ethanol, that has a relatively high boiling point compared to, say, propane, which is similar in size, but doesn't have that hydrogen bonding potential, right? So the alcohol are the boiling point of that alcohol is way higher than the boiling point of that. For dimethyl ether, again, sort of similarly sized, we now have that oxygen that has its lone pairs, but again, there's no hydrogen bond donor there. Because of that, ether molecules can't interact with one another very strongly. So its boiling point is quite a bit lower than it would be if it was an alcohol, much closer to that of an alkane, although it is a little bit higher, you can see, because, polarizability of those electron clouds. So a big factor in the relative boiling point of ethers is just going to be the size. So the dominant force there are going to be those London dispersion forces. And so just like we saw with our alkanes, when we increase the size of our ether, we do still see an increase in the boiling point because there's more surface area. Remember, that was the key for the London dispersion forces. And so, yeah, so the bigger it is, the higher the boiling point. Because of their relatively low boiling point, ethers are really good solvents for organic reactions. And what makes them good is that they're going to be easy to remove, right? Having that low boiling point means that you can sort of boil it off and then you're left with what you want. They're also fairly unreactive. We're going to see that ethers don't really have many reactions that are associated with them. Most of the reactions we're going to talk about are ways to prepare ethers, not things that we can do with ethers. One of the other features of an ether that does make it good is, unlike the other low boiling point substances, for example, straight up an alkane, using that as a solvent, those are extremely nonpolar. Ethers are relatively nonpolar, but they do still have these lone pairs which can accept or stabilize positive charge. So classic use of an ether would be in a Grignard reaction, where you need something to stabilize that magnesium that has the positive charge. So ethers are great, right? And then again, plus you can really easily get rid of it at the end. Another really cool use of ethers, and honestly, I can't imagine that the ACS can throw you something too crazy about this, but nonetheless, I think it's really cool, so we're going to go over it, is this idea of a crown ether. So this is like a circular ether. Notice that they have this repeating units going on, and then you have your oxygen in the middle. So then, it's basically just a circular, a circle made up of many ether parts, right? And so these are called crown ethers. The numbers represent, the first number would represent just the total number of atoms in the ring, or I guess excluding the hydrogens, right? So carbons and oxygens in the ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, followed by crown. And then the last number corresponds to how many are actually oxygens that are in the ring. 1, 2, right? So 12 crown 4 would be this molecule here. These are the cool thing about them, if you want to look at the electron density, is what they do is they create this sort of circle where the inside of the circle is where all that negative charge or partial negative charge on the oxygen atoms are. So these can be used to trap ions. Okay, so that you sort of build them in such a way that they're a perfect size to trap a particular ion. So for example, the 12 crown 4 crown ether is perfect to fit a lithium ion in there. 15 crown 5 is perfect to fit the sodium ion, and then you get a little bit bigger for the 18 crown 6, and that will perfectly get solvate or trap that potassium ion.